everyone. So, we are almost towards the end of this course. What we have been discussing? We have been discussing salient features of finite element method. Now, you see, if you recall, these are the different kinds of elements we may have different depending on the dimensions of the problem and what kind of accuracy we need. We already discussed the formulation for this element. Then formulation, in the sense, we have a general formulation, if you recall, that your stiffness matrix is equal to B transpose integration over domain B transpose dB. Now, what is B? This integration over the entire domain. Now, depending on whether the problem is 1 dimension, 2 dimension, 3 dimension, this integration will be over the entire domain. And similarly, depending on what kind of problem you are doing, whether it is a truss problem, beam problem, or some other problems, these D will be different. And then B depends on what are the degrees of freedom you have at every nodes, how these degrees of freedoms are interpolated, or how those degrees of freedom are represented through a functional form. Through a function that depends, that gives you B. So, B essentially the strain displacement relation, not necessarily strain displacement relation, but the examples that we have been discussing in that context, B is strain displacement relation, right? Depends, we will see towards the end of this lecture that depending on if your problem is different, degrees of freedoms are different, then the interpretation of B will be different, but essentially the B is you have some primary variable, you have some degrees of freedom. That degrees of freedom in our case is displacement. So, you have degrees of freedom, and their degrees of freedoms at every nodes are interpolated that is represented through a function, and then when we calculate the derivative of that functions, that gives you B. Okay. So, this is the general form of stiffness matrix. Similarly, we can have a general form of load vector as well. We discussed that. Now, we can have we have seen how to, for a triangular elements, for a quadrilateral elements, we will briefly see if the elements is not, if you have a 6 noded triangle and if you have a 4 noded say tetrahedron in 3 dimension, then how to get those shape functions. The process exactly will be the same. We will see that shortly. Now, one important point, okay, let us wait for that. Now, let us start with let us see if our element is a 6 noded element, then what will happen. Now, if it is a 6 noded element, then draw a 6 noded triangle. Then we have, these are the nodes. The process will exactly be same. I am repeating this process just because. Okay. So, again you have a node number, for instance, suppose this is 1, 2, 3 and then 4, 5, 6. We already have seen then how you number these nodes in the context of one dimensional problem, how we number the nodes. Depending on that, you get the stiffness matrix, the population of the stiffness matrix, right. You can be a number you can number those elements in such a way that your stiffness matrix, you get a banded stiffness matrix, and banded stiffness matrix always better to have from the computational perspective. Now, so these are the node numbers. Similarly, you can have, say, these are the degrees of freedom at every node. So, you can have degrees of freedom, say here it is E1, U2, E1, U2, E1, V1, then here it is U2, U2, then V2, V2, U3, U3, V3 and so on, and then U4, U4, V4, U5, then V5, then we have U6, U6 and then V6. Okay. Now, the generic approach for all the whatever elements you are using, general approach will be same. Now, you have 2 degrees of freedom here, U and V, though are 2 degrees of independent degrees of freedom, right. Independence, this displacement quantity, and U will be approximated as. Now, since you have 6 nodes here, so we have information from 6 nodes. So, we can use, say, A plus Bx plus Cy plus Dx square plus Exy plus f y square. We will shortly see what, when we approximate a function through a polynomial, then what are the terms to be considered. For instance, see, we can have just 6 nodes only. So, information from 6 nodes are available. So, in the approximation we can have 6 unknown. Now, the question is how you we can have a several some other approximation where your polynomials are different, the monomials are different. Instead of say x, we do not take the term x and we take a different term, but keeping the number of unknown same. Is that enough? Is that right? We will see that shortly. So, similarly you have this, and similarly we also have this. So, then what you can recall, what is the approach we did? The conditions that we have is E1 is equal to A plus B x 1 plus C y 1 plus D x 1 square plus E x 1 y 1 plus f y 1 square. Similarly, we have U 6 is equal to A plus B x 6 plus C y 6 plus D x 6 square plus E x 6 y 6 plus f y 6 square, right. So, this gives you 6 equations, this gives you 6 equations, and then we have 6 unknown. We can obtain those 6 unknowns, and when we have these 6 unknown, finally u, which is a function of x and y, can be represented as ni u I. Okay. So, ni is the shape function, it is a function of x and y. Similarly, v at any point x and y can be represented as ni and vi. ui and vi are the nodal values, okay, and ni is a function of x and y. Now, naturally we can look at, by looking at this. Okay. Now, let us compare this with these with the 3 noded triangle. 3 noded triangle also, we already derived the expressions for n, right. This is node number 1, node number 2 and node number 3, and there also we had u is equal to u x y is equal to ni u y. It is expression is same, and v also v x y is equal to ni v y. Okay. Now, but then only difference is here you have summation over only 3 nodes, here you have summation over only 6 nodes. Okay. Now, there is another major difference. The difference is, if you recall, when we constructed this a function for this element, what was the initial approximation of field variable? Approximation 1, u is equal to a plus bx plus c y. So, u that time, similarly v. So, u was essentially a linear function of x and linear function of y, right. But now, here we have u is that much we could afford for this 3 noded triangle, because we had only 3 nodes, therefore, the informations are available only for 3 nodes, which will help us to calculate only 3 unknown. That was the reason why we had just only linear approximation. But whereas here we have 6 nodes, so we can approximate this field variable with a quadratic approximation like this. Then what is the consequence of that? Consequence of that is other consequence we will see when we talk about convergence, but immediate consequence is, you see, in this case, if you approximate, say, if you calculate strain, say epsilon x, if you recall, epsilon work x is the strain in x direction, right, longitudinal strain, normal strain in x direction, that is equal to, so if you have du dx, then this becomes b. Similarly, epsilon y becomes dv dx, okay, this becomes similar, a constant like this, that may not be b, but some other constant, some constant. Okay. And similarly, if we have, say, epsilon x y, which is, if you recall, half of del v del x plus del u del y, this will be also because some constant. Okay, because both u and v are the linear function of x and y. So, what this means? This means that your entire strain field, now the strain field is represented as, if you have a strain like this, in 2 dimension. So, this is epsilon x if write epsilon x, epsilon xx, epsilon xy, epsilon xy, epsilon yy, or epsilon xy and yx are same, this is the entire strain field. This entire strain field is equal to constant, right? Constant means not this the constant, this constant. Okay. Now, so you have a triangle, you have an element, within that element your strain field is constant, and that is the reason this element is called constant. Let us use different color. This element is called constant strain triangle or CST. If you see any finite element book, probably the initial phases, the elements you will come across is constant strain triangle. Now, these elements have some disadvantages, advantage or disadvantage. Those aspects will not discuss here. You yourself apply, you yourself write a code for finite element method. The way we had written a code for 1D bar and beam element, you can do that exercise for higher dimension as well, and then use constant strain triangle and then see yourself the results what you are getting, how the results is closer to the actual results. Okay. So, there it says the strain is constant along the within the element. Then therefore, naturally if your strain is constant, stress is constant, everything is constant, right? Now, strain and stress are constant. Now, the thing is which, I mean, by intuition you can say if you have a body, then you discretize that body into small elements, several set of elements, and then within every element you are assuming this, if you use this element, it gives you strains, constant strain within the element, and therefore, if you use the larger size of the element, then what happens? The strain is constant over a larger area, which may not be possible, which may not be consistent with the loading field on the structure. Therefore, this element can give you a result, but the condition is at a very limiting case when these elements size is very small. Okay. Now, even with smaller elements, whether you get closure results or not, and what are the difficulties you face while solving a problem using this element, that will not discuss here. I leave it to you, you find that yourself. Now, but when we have this triangle where the u is essentially a quadratic function of x and y, and then if you calculate epsilon x here, epsilon x for in this case, so epsilon x will be b plus 2 dx plus e y. So, it is a linear function of x and y. So, this is not constant. Similarly, you can have epsilon y and epsilon x y. So, here you that restriction, the strain is constant, that restriction is not applicable here. Okay. So, you get varying strain field even within an element. Now, once you have this ni ui, then next is again the same approach. Calculate strain. Epsilon x will be your del ni del x into ui, and epsilon y will be del ni del y into vi, and epsilon x y will be half of del ni del del yi del y into ui plus del ni del x into vi. So, this gives you a strain displacement relation. So, this thing you can write as epsilon is equal to some B matrix into u and v, right, ui and vi. So, this gives you the B matrix strain displacement relation, where B matrix is essentially what will be the size of the B matrix in this case. The size of the B matrix will be, you see here you have here total degrees of freedom is 12. So, size of the B matrix will be 2 into 12, right. This is the size of the B matrix, and size of this will be 12 cross 1, and this will be Okay, so this is how you can this 3 into 3 into 3 into 12 and this will be 3 into 1, the strain will be 3 into 1. So, this is how you can have this. Once you have B matrix, D is the constitutive relation, strain displacement relation, substitute that in the stiffness expression and integrate it over the entire domain, you get the stiffness matrix for this element. Now, a similar exercise you can do if your element is in 3 dimension. So, another thing you must do is, once you get these shape functions and then the properties of the shape function we discussed. First thing, you have to plot these shape functions and then see whether the shape functions satisfy the Kronecker delta property or not, whether the shape function satisfy partition of unity property or not. You take any arbitrary point and sum all the shape functions, whether they are giving you 1 or not. So, these are the some properties that shape function must satisfy, and this is a check. See, by construction it should satisfy, but when you write a code, then these are the some checks that you should perform to check whether your computation, the codes are written properly or not. Okay. Now, similarly, if we have suppose if we have a element in 3 dimension, for instance, if we have this kind of element, say tetrahedron, we have 3 elements, 3 nodes and one another, total 4 nodes we have. So, if we have this kind of elements, then what happen? So, okay. So, what we have is we have say then and then another element is this, another node is this. So, we have total one node is here and another node is here. So, our elements is essentially this, right? Elements is this. Now, similarly, we have to first give the numbering of the nodes, say 1, 2, 3, 4. We will not discuss. Now that every nodes, every points you have. Now, since it is in 3 dimension, so every points you have 3 degrees of freedom, right? So, this is your U1, U2, then U2, then you can have V2 and then you can have W2. So, U1, V1 and then W1 and so on. Similarly, here you have U3, then V3, then W3 and then U4, V4 and then similarly W4. So, at every point you have 3 degrees of freedom. Then next is we have to construct, these are the values at the nodal points. Now, we have to get a value at the intermediate point within the element. For that, we have to represent them all this nodal value through a function, and for that assume u, which is a function of x, y, z both, say x, y, z both, you have to approximate it. Say it is a plus b x plus c y plus d z. Okay. And then you have 4 nodes. So, essentially we are getting information from 4 nodes. So, 4 equations we can have for every degree of freedom. So, that is why we have to restrict it a, b, c, d. Now, then substitute u1 is equal to a plus b x1 plus c y1 plus d z1 and so on. Get this get u4 is equal to a plus b x4 plus c y4 plus d z4. So, get this, solve it, substitute a, b, c, d in this expression and finally get u x, y, z is a function of n(i), which is a function of x, y, z and then u y, and similarly for v I and w I. So, once we have this displacement approximated like this, again you can check all the properties of the shape functions. Then you have to differentiate it to get the strain, and that gives you strain displacement relation B, and again you have to substitute that in this equation B transpose dB, and then we get integrate over it, get the stiffness. Okay. Now, in this case what would be the, this is a 3-dimensional problem. So, what would be the size of D? Size of D will be 6 by 6. Size of D will be, if you recall, in a 3-dimensional space for plane strain and plane stress idealization, the size of D was 3 by 3, because you have either 3 stresses or 3 strain. Now, but in this case we have all 6 components of stresses and 6 components of strain. So, constitutive relation will be 6 by 6. Okay. And then what is the how many degrees of freedom, total how many degrees of freedom we have? At every node we have 3 degrees of freedom, total 4 node. So, we have total 12 degrees of freedom. So, B matrix will be 6 cross 12, and then B transpose natural will be 12 cross 6. So, essentially this gives you a matrix which is 12 cross 12, the stiffness matrix, size of the stiffness matrix. Okay. So, once we have the stiffness matrix, again similar exercise we can do for loading, and then we get the expression K U is equal to F, and rest of the things are same. You have to solve it. Okay. So, this is how we can do it for any other any degrees, any other nodes as well, but there are some efficient ways also to write the to construct these F functions. Now, all these F functions, the common thing, if you see whether it is for 1D, 2D or 3D, 3 dimension, when we construct this F function, we assume that displacement, the degrees of freedoms, the field variable is approximated through a polynomial. But again, depending on that is the most of the time, that is the general thing, common thing we take. There are reasons for that. We are not going into that theory here, but just to inform you, there are cases you can think of not having polynomial expression for your field variables. You can have a similar different kinds of expression for your field variables. Okay. Now, so you can have in 3 dimension, you can have any other degrees of freedoms like this, but the essence will remain same. Once you have the degrees of freedom, approximate them, give a function representation of those degrees of freedom through which we can get the values at any intermediate point, substitute that in the expression and get the corresponding stiffness matrix. Okay. Now, then yes, this is important. You see, just now I was telling you when you approximate these field variables, then what are the elements you should take. One thing is the number of elements in the approximation, the number of unknown in the approximation, that depends on how many nodes we have, how many informations we have from the element, right? This is one thing. But the second thing is then can we take any arbitrary combination of x and y, keeping the total number of unknowns same? Actually not. So, this gives you a guideline what are the points you have to take. This is a Pascal triangle. It tells you that it is given in 2 dimension. Now, but the similar thing we can have in 6 dimension. Okay, 3 dimension. Now, it tells you that if it is constant, then of course you have just one term constant. If it is linear approximation, then you have to use all these term you have to use one term associated with constant, then one term for dependency x dependent, and one term associated to y. Okay, and then if it is quadratic, so here how many terms you have? You have y term. Now, if it is quadratic, then you have to take all the terms up to this. Means you have to take, if you recall, for quadratic we assume, when we assume that y is a quadratic, we took a plus bx plus cy plus dx square plus exy plus fy square. So, total 6 terms are taken, all these terms are taken. Similarly, if you have a cubic polynomial, then you have to take all these 10 terms to make it cubic in a way that you should not have any biasness in x direction or y direction. For instance, if I do not take this, instead of that, if I take plus f say x cube, Okay. Still we have only 6 unknown, and we have 6 equations, we can get these unknowns, but the thing is we have, by doing so we have introduced a biasness in this in the direction. So, this is not a complete polynomial, completeness in with respect to both the coordinate axis. So, when you take this when you follow this rule, then you have a polynomial, you have an expression which is complete, and that is very important for getting convergence. We will discuss the convergence shortly. What is convergence? So, that is the reason why when you take this approximation, you have to be careful what are the term you take. Okay. Now, this is for Pascal triangle, and the thing is isoparametric formulation. This is important, you know. You see all the cases where we discussed so far, what we did is we know what is the values of coordinates, we assume it is a 1D element, we assume it is a triangular element, we assume it is a 4 noded element. But you know what happens many times that for instance if you have a domain like this, say anything, if you have a domain like this, say for instance if you have a domain like this, okay, a domain, any arbitrary domain like this, and you discretize this domain into say set of elements, okay, these are your elements, 4 noded element, okay, for every node these are your for this is the boundary, this red is the boundary, and for every these are the nodes. Okay. Now, you recall when we talk about these quadrilateral elements, 4 noded elements, then we assume if you recall there again, if I go back to yes, you can go back to 4 noded quadrilateral, we assume that this length is L and this length is H, right. So, it is a perfect rectangle, at least that was the thing that we assume while deriving these functions, but it may not be possible every time, right. So, what we have to do is suppose in this case your elements are like this, elements are essentially, then if you draw one element, your element will be like this. Your element will be like this, which has 4 nodes. These are the nodes we have, but they are not rectangular. Okay. Then what happens to this case? How do you calculate the stiffness matrix for this? And this is just an example I am giving you. It happens almost all the time. Your elements are not perfect square or perfect rectangle, or depending on the what size you are, what shape you are taking, it is not perfect in that sense. So, what we can do is, suppose we can define two space, one is parametric space where your element is a, in this case if you look at, is a perfect square, which is this coordinate is it is 2 by 2 square, you can have 1 by 1 square. Okay. Now, then what happens? This is your parametric space, and then you have an actual element like this whose coordinates are x1, y1, x2, y2 and so on. If you recall, in the previous cases we wrote the shape function in terms of x1, y1, stiffness matrix of x1, y1 and so on, but now this is directly not possible because the shape of the element is not perfectly rectangle. So, what we can do is we can define a parametric space like this, and then we have an actual element like this, and then we can map between this space and get all the, then approximate your field variables over this with respect to the parametric coordinate xi and eta, and then find a relation between xi, eta and x, y through a map like this, and then do all this approximation integration on this element and preserve this map to get the stiffness matrix, final stiffness matrix of this element. Okay. So, this is called isoparametric formulation. Okay. Why it is called isoparametric? Let us not bother about right now. Okay, isoparametric is essentially, okay, we will come to this point shortly. Now, this is the isoparametric formulation. Now, or the concept. So, there exists a formulation through which even your elements are not perfectly square, perfectly rectangle. You can map this to an element in a parametric space and do all the exercise and get final approximation, final stiffness matrix of this element. Okay. Now, this kind of formulation is also exists and this is a very common. Now, this is important, convergence. Okay. Now, before we talk about convergence, let us talk about some of the important you see, essentially what we have essentially we are solving some phenomena, some physical process. Like now, what happens? For instance, if I give you an example, suppose I have an area, I have an arbitrary area like this. Arbitrary area like this. Now, I want to determine what is the area of this shape. Okay. Numerically, it is not a square, it is not a rectangle. So, we do not know the closed form relation of the area and its geometric parameter. So, what we can do is the common thing we can do is we can divide it into some squares like this. Okay. And then what we do is we calculate the number of squares. Suppose for this it is full square, we take the full area, and this is how much percentage of square, depending on that we take the area, and then we sum them, we get the area of this entire shape, right. Now, one common sense tells you that if you take smaller squares, then you get your area computation will be better. So, if you take further smaller square, for instance, if you take further smaller square and then you compute the area, so your computation will be more accurate, more closer to the actual value. So, in a sense what we say is, when we take further smaller square means what? When we are taking, if we just bring the analogy that every square is essentially an element. Okay. So, when we take larger square, the element sizes are larger, but the number of elements are small. So, if we keep on reducing the number of squares and reducing the size of the squares, then what will happen? Your number of elements increases, and also you get better accuracy, right, in the context of this problem. Now, if you keep on doing that, and at some point what will happen that this, if we plot it, what will happen that if we increase the if we plot and curve with x axis the number of elements and y axis is the actual value, then we will see as the number of elements becomes more, the computed area is approaches to the exact value, right. So, this is then when we say that these approaches to an exact value means it is converging to the exact value. Okay. So, in every computation, and this is just to bring an analogy, and finite element method exactly we do that. We divide the entire into small elements, and then we write the equation for each element and then assemble them to get the solution of the entire system. Now, naturally very similar to that, if we increase the number of elements, the intuition says that your predictions, the computations from computation will be closer to your actual value, and this entire thing is this is called convergence. Means if you keep on increasing the elements, your prediction will converge to the actual result. Okay, will be closer to the actual results. Or in other way we can say that if we keep on increasing the number of elements or reducing the size of the elements, the error between the predictions from your finite element simulation and the actual results, so this error will decrease, right. So, this is called convergence. Now, the convergence generally can be achieved in two ways. One convergence is called H-convergence. For instance, in this case what we have done is we have just increased the number of elements, right, or decreases, we have decreased the size of the element. Say size of the element is, if we H is the characteristic size of the element, then we say that if this convergence is achieved in this case, if H is the size of the square, each square, so this convergence is achieved by reducing the H, that is it, keeping all are squares only, but larger square and smaller squares. So, this convergence is achieved, the error is being reduced by reducing the size of the elements. This convergence is called H-convergence. This convergence means the convergence achieved by reducing the size of the element. Okay. Now, You can have another convergence which is called P-convergence. What is it? The P-convergence is now you go back to this set of elements. You see what happened in this case? If you recall, in this case your displacement field was linear. In this case your displacement field was quadratic. Similarly, here also you will see in this case your displacement will be linear, in this case displacement will be quadratic. So, you can have an element where displacement field is cubic. You can have element where displacement field is 4th order and 5th order and so on. So, if you increase the order of this displacement field, means the order of the approximation, then what happens? Then also you can get convergence, and this convergence is called P-convergence. P stands for the order of the approximation. So, here linear your P is equal to 1, here quadratic P is equal to 2 and so on. You can have a cubic with P is equal to 3. So, if we increase the higher ordered elements, then also you get a results which is closer to the actual results. Then this is called the P-convergence. Okay. So, convergence can be achieved in both way, either you reduce the number of elements or increase the order of the approximation. Okay. Now, with this, this is called convergence. Okay. Now, convergence is a very important part in finite element method, and if you take any book, there is a chapter given on convergence, different kinds of convergence, what are the estimates of convergence, how to see whether the convergence can be achieved or not, what are the tests, what are the error analysis, everything is given there. Now, here our objective, what we have been doing in this week is to give you the information that these other things exist, and you have to go through the books to read what exactly it says. Okay. Now, now the question is, you see here another important thing is convergence. Suppose, for instance, you have here number of elements, okay, elements, and this is error. Okay. Now, suppose this is your actual results. Okay. Now, essence is if you increase the number of elements, you can get your error should be reduced. This is not the actual result. Suppose this is the it is the actual result. Now, the convergence, the essence is if you increase the number of elements, the results should converge to the prediction should converge to the actual results. Now, you see it can converge to the actual result like this. This is also converging to the actual results. Now, this is also converging to the actual results. Then this is also converging to the actual results. Okay, there are many ways your prediction can converge to the actual results. Then the question is whether all these convergence are acceptable convergence or not, or in finite element framework what convergence do we expect. Now, before I discuss that, before I say that, you see what exactly we are doing. If you take any system which is a continuous system, and if you might have read dynamics course that or any other structural mechanics course, that if you take a continuous system is essentially a collection of infinite number of points, right? Now, if you take a point in 3-dimensional space, every point has 6 degrees of freedom. In 2-dimensional space, it has 3 degrees of freedom, right? Now, when you have a continuous system, which is a collection of infinite number of points, and every point having 6 degrees of freedom, naturally a continuous system having infinite degrees of freedom, right? So, infinite way, there is infinite possibilities that the structure can deform, right? A continuous system can deform. But then what you are doing when you discretize a system, then you are essentially what we are doing. When we discretize a system, then actual continuous system is essentially is a collection of infinite number of points, but we are representing that through a finite number of points. Discretization is essentially that. When we say that an element is, for instance, if we take this case, in this case, your actual points, actual area was this, which is in continuous system having infinite number of points, thereby having infinite number of degrees of freedom. But now this is represented by just set of points, the collection of these points 1, 2, 3, 4 only 16 points. So, when we discretize it, this is a continuous system, this is a continuous system, and this is a discrete system. In the discrete system, essentially we have a finite number of points. When you have a finite number of points, then what is essentially we are doing? We are reducing the degrees of freedom, right. So, every point has 6 degrees of freedom, every point has 3 degrees of freedom, 16 points, 48 degrees of freedom. But actual system has infinite degrees of freedom. When you discretize it, we are allowing only 48 degrees of freedom. When we reduce the degrees of freedom, so essentially what we are doing? We are restricting the freedom of this object to deform. The way it may deform, it can deform in a continuous system. We are restricting that deformation. Means we are making our system stiffer compared to the continuous system. When you make your system stiffer, then when you solve for displacement, what do we expect? Your displacement is more than the actual system or the less than the actual system? Obviously, less than the actual system, because always we are dealing with a stiff system. If it is the case, then if you plot, now if this is the case, then if you plot, it is number of elements, and this is actual, this is your computed results, and if this is your actual results, then always the results we get less than the actual results. We are talking about displacement less than the actual value, because we are always dealing with a stiff system. And if you increase the number of elements, you are slowly increasing the degrees of freedom. You are making this structure from stiffer to stiff, and then more flexible, then more flexible. So, this will converge to this. This is a typical characteristic in convergence in this finite element method. So, it is always bounded from top. Okay. So, this is the way we get the convergence for the displacement. But again, okay. So, we won't get the convergence any haphazard way. So, this is the convergence. Now, then quickly, one important thing is still left, that is integration. We'll discuss that integration. You see, when we say that your stiffness matrix is integration B transpose dB, d transpose dB d omega. So, this has to be integrated over the domain. Now, the domain is, it can have a different kinds of domain. So, this integration may not be possible always, most of the time in a closed form. So, we have to do it in a numerical, following a numerical technique, and that is an important aspect in finite element method. We'll discuss that integration in the last class, in the next class. So, I stop here today. See you in the next class. Thank you.